Hello and welcome to week 6 and lecture 30 of the course Computational Complexity. So in the last week we saw randomized complexity classes RP, co-RP, ZPP and BPP. Today in this lecture we will see a new class called PP, which stands for probabilistic polynomial time, and then we will elaborate a bit on how BPP is boosted, how the probability of success is boosted in the case of BPP, and we'll contrast between BPP and PP, and we will also compare all the randomized classes towards the end of this lecture. Okay, right. So what is PP? PP stands for probabilistic polynomial time. Okay, so it's a very simplistic name. It doesn't give you any clue what it is, except that it is a probabilistic class. So basically, these are the class of languages for which there is a probabilistic polynomial time Turing machine, just like what we had for RP, co-RP, BPP, and so on. But when X is in the language, the probability of acceptance is just above half, or just greater than or equal to half. And when X is less than, or X is not in the language, the probability of acceptance is strictly less than half. So this is how PP is defined. So contrast this with BPP. Okay, so BPP, the way we defined it, I think it was 2/3, and if X is not in the language, this was less than 1/3. So we could just go back and refer back to our notes. Two-thirds and one-thirds, right? So this is what we used. So in the case of BPP, it is 2/3 and 1/3. In the case of PP, it is greater than or equal to half and strictly less than half. So notice what happens here. In the case of PP, there is really no gap. So if exactly with half probability a certain input is accepted, and even if one of the random strings decide to flip, right? So suppose there are all the randomness that is used are of 10 bit strings long, right? So 10 bits long, which means there are 2 power 10, 1024 possible random bit strings. If exactly half of them, 512, lead to accept and 512 lead to reject, X would be in the language in the case of if it's a PP machine. Even if one of them becomes reject from accept, right? So then it will be 511 accept and 513 reject. In that case, it would be X not in the language, right? So it is a very fragile situation there. Whereas in the case of BPP, the gap, there is a significant gap. When X is not in the language, when X is in the language, it has to be accepted with probability at least 2/3, and when X is not in the language, it is at most 1/3, right? I mentioned that this 2/3 and 1/3 are arbitrary, and that we could increase or reduce the gap, but still even then there will always be a gap, right? So the boosting, we said that it can be boosted in such a way that the probability for accept X is in the language is half plus 1 by Px, and X is not in the language is half minus 1 by Px. So still there is an inverse polynomial gap between accept and reject, whereas in the case of PP there is absolutely no gap, right? So this is a difference between the two classes PP and BPP. Right. So one thing to note, the first thing to note is that RP is contained in PP, because RP just requires when X is in the language, the probability of acceptance to be at least half. When X is not in the language, the probability of acceptance should be 0. So an RP machine by definition is also a decider for PP, right? Because 0 is less than half. Right? And another thing to note is that the value half is an arbitrary choice. So instead, if I had a machine that accepts, you may, if you look at other references, you may see some things like this: X is in the language, then probability of acceptance is strictly greater or 3/4 for instance. Okay, sorry, I'll use another pen. 3/4, and when x is not in the language, probability of acceptance is less than 3/4, right? So when I say arbitrary, you could move the half bar to anywhere, like let's say 3/4 or 1/4 or whatever. This is not really, it is not very difficult to see why this can be done. But even when the bar is moved, the accept and reject remain very close to the bar, right? So there is no gap between accept and reject. So even if one random bit flips from one the accept to the reject or reject to the accept, the output flips. So just that the where the bar is, that can be moved. Whereas in the case of BPP, it's like there is a gap, and of course the gap can also be shifted a bit, but there will always be a gap. So even if you bring it closer, it will still not be the same. There will always be a gap in the case of BPP. However, in the case of PP, the gap is not there, but where we want the bar to be, the threshold between accept and non-accept, or x being in the language and not being in the language, this can be moved. The point, one way to see this is you could just simply declare half the random bits to be leading to an acceptance, so that only the rest of the half are actually going to determine the outcome of the string. So then automatically you have half, and the rest half now, if among the rest of the half, if half leads to accept and half leads to reject, then you have a situation like 3/4 is the bar for acceptance, right? So that's a very high level idea, but that's how we can move the bar from half to 3/4, or maybe to 9/10, or maybe to 1/4, right? So you could just make the similar kinds of argument, right? And boosting, right? So whenever I mentioned earlier classes, we said about boosting. In fact, I will also elaborate the BPP boosting a bit in this lecture. However, there is no known boosting situation in the case of PP. This is because there is no gap, so there is no way to repeat and kind of gain more information, because the situation is very close. So there is no boosting available. And another point to note is that NP is contained in PP, right? So if there is one certificate, so NP, what does it say? If X is in, if L is in NP, then if X is in L, then there is at least one accepting string, right? One proof or witness or certificate. But if X is not in the language, then there is no such certificate that will lead to an acceptance, right? So you have a verifier machine that will accept or not accept these certificates. In the case of, so we can basically convert the verifier or build on the verifier as a randomized polynomial time machine to show that L is in PP as well. Okay, so how do we do that? So for the language L that is in NP, let V be the verifier, right? B be the verifier. Now suppose if X is in the language L, let Y be the certificate. Okay, so if X is in L, then Y, there will be a certificate, let us call it Y. Now if an input has a certain length, let's say I'm denoting X with vertical bars around it to denote the length of the string X. Let the certificate length be P of X, so where P is some polynomial, right? So that by the definition of NP, the certificate length has to be polynomial in the length of the input. So let the certificate length be P of X. Now, so V is the verifier and P is the length of the certificate, okay? P of the length of the input. Now consider a randomized Turing machine M, okay? So which takes as input X as well as a random string as input, right? So randomized Turing machine meaning it just takes as input as some randomness. After that it just does some calculation based on the input as well as a random string, right? So it is just like this. So there will be M, right? There will be the input X and there will be some random string r, and based on this there will be the output, right? This is how randomized Turing machines work. So and what M does is completely deterministic once it has the random bits, right? So the randomness is input through the random bits R. Okay. So now consider a randomized Turing machine M that takes its bit string R as input, where the length of R is 1 more than the length of the verifier. Okay, we'll see why that is required, why it has to be 1 more than the length of the verifier. So right as of now, M is a machine that we are constructing. We'll see how we use V in the construction of M. Okay. So what does M do? So if R is of the form, the leading bit of R is 0, right? Let's say R is 0 followed by some string U, right? Where U is of length px, right? So U will automatically be of length px because R is of length px plus 1, right? Then let, so what is mx r, right? Or mx, sorry, mxr, which is equal to mx 0u, right? We will define it to be v of xu. So the first bit is 0, right? Then we just run the verifier, right, on the rest of it. Okay. So whatever the verifier does, if r is equal to 1u, right, then r equal to 1u, there are two sub cases. Okay. If u is equal to 1 1 1 all ones, then reject. If u is not equal to all ones, then, so when I say reject, I meant mxr equal to reject, otherwise this is equal to accept. Okay. So basically, for all the inputs which start with 1, for all r that start with 1, we accept except for a single string which is all one string. Okay. Let's see why we do that. So let's try to understand. So what is happening here? So amongst all the bit strings that start with 1, everything leads to an acceptance except one string, okay, which is all one string. So let us compute the probability of a string getting accepted. Okay, so let's compute the probability. What is the probability of m accepting x? There are two cases. One, if x is in L, so let's, so in other words, another way to see this is how many random bit strings lead to accepting x, right? So let's say when x is in L, so how many random bit strings lead to m accepting x? So for all the random bit strings that start with 1, all of them accept except 1, right? So there are total 2 power px many such strings. All of them accept minus 1. Right? This is just the strings that begin with 1. And plus number of certificates. So right? So all of them accept 2 power px minus 1, and then when r begins with 0, all the certificates that lead, all the correct certificates that lead to x being accepted, right? So divided by total number of random bit strings, which is 2 power px plus 1, so where 1 here is in the exponent. So notice that, so in fact this is actually true for everything, not just x is in L. But when x is in L, so this is the probability, right? Probability of acceptance. When x is in L, what happens is there is at least one certificate, right? Number of certificates is at least 1. So probability of acceptance is at least, so this one and this one will at least cancel, so then you have 2 power px divided by 2 power px plus 1, which means this is at least half, right? It's at least half. And when x is not in L, number of certificates is actually equal to 0. There is no certificates that lead to a string getting accepted. So probability of certificates or probability of acceptance will be just, this entire term will go, the certificates thing will vanish. This is 2 power px minus 1 divided by 2 power px plus 1. So this is just below half, just below the half mark. So this is strictly less than half. So sorry, right? So which means it's a PP machine that we have constructed. When x is in the language, the probability of acceptance is greater than or equal to half, and when x is not in the language, the probability of acceptance is strictly less than half. So it's a PP machine. So we took a arbitrary NP language and we showed that it is in PP. So NP is contained in PP. Okay. So this is about PP and NP containing in PP. And it is also, it's not very difficult to see that BPP is also contained in PP, right? Why is that? This is because as I said at the beginning, this is the PP, this is the BPP numbers. So any BPP machine automatically qualifies to be a PP machine. The probability of acceptance is at least 2/3 and at most 1/3. So at least 2/3 means it's all obviously above 1/2. At most 1/3 is all obviously strictly less than 1/2. So a BPP machine is already a PP machine. So BPP is also contained in PP. BPP is contained in PP. It's not very difficult to see, right? Right. So yeah. Now I want to go on to the boosting part of BPP. Again, last lecture I mentioned it briefly, but I want to elaborate it a bit more. So because it is more relevant to what is going to come after this. So this is just recalling the definition of BPP, right? This is what I wrote in the previous lecture. L is in BPP, there is a probabilistic polynomial time machine such that the probability of acceptance is at least 2/3 when x is in the language, and at most 2/3, at most 1/3 if x is not in the language. And the boosting result is that if there is a polynomial time machine that uses randomness such that if it accepts with probability half plus 1 by px, right? So 1 by inverse polynomial could be some small number, right? It could be 0.001 or something, right? Again, a constant is better than inverse polynomial. This, and when x is not in the language, it is the probability of acceptance is upper bounded by half minus 1 by px, right? So there is a gap, but a smaller gap, not 2/3, 1/3 gap. It is just like 1 by px above half and 1 by px below half. Right? So there is a 2 by px gap. Even this gap can be boosted to a bigger one. That's what we want to show. So even if this is the situation for some polynomial px, right, then that language is said to be in BPP. So why is that language in BPP? Because we can boost the probability of success in this machine to get the 2/3 1/3 bound. Okay, so we'll see how to boost the probability of error, or improve the probability of, or reduce the probability of error, or improve the probability of success in order to get to the 2/3 1/3 mark. So here you can see the error is like half minus 1 by px, right? Even when it is something is in the language, just above half gets accepted. So the probability of success is just above half. Probability of error is just below half. And when x is not in the language, again it is the probability of acceptance is actually probability of error, right? So that is just below half, right? So how can this be boosted? What we use is a standard kind of technique from probability theory, and also very much used in randomized algorithms, called Chernoff bound. So if there are n independent 0-1 random variables, right, where, so these are n independent 0-1 random variables, they're independent, they have the same distribution, each one of them equal to 1 with probability rho, right, x1 x2 up to xn, and each one of them being 0 with probability 1 minus rho, obviously, because they can only be 0 or 1. So if they are not 1, they have to be 0. Now let us consider the sum of all of x1 x2 up to xn. The sum is let's say x, and mu be the expectation of the sum, and expectation of the sum of a set of bunch of random variables is nothing but the individual expectations, but the individual expectation of each of them is rho, because 0 into 1 minus rho plus 1 into rho is just simply rho, right? So expectation of x1 is rho, x2 is rho, and so on. So expectation of x is n times rho, which is n rho, right? In that case, what does Chernoff bound say? Chernoff bound says that the probability, there are two forms of Chernoff bound, I am stating both here, that x is epsilon less than the expectation, right? So again, mu is the expectation of x, is e power epsilon squared divided by 2n. That is one form. Sorry. So the main thing is that, again, there are multiple forms of the Chernoff bound, and if you look at Wikipedia or other sources, you may find different forms. They're all powerful. All of them are powerful, and you may end up, there is a chance that you get confused between them. Many people do that, so don't be worried about that. The key thing to note is that the probability of x, even epsilon being slightly away from the mean, even epsilon away from the mean, even that is exponentially small. So the point is that this epsilon squared by 2n appears in the exponent of e. So as long as it is slightly away from the mean, it just drops off significantly. That is the key thing that one has to focus. So like I drew it in this the previous lecture, right? So if the mu is the mean, then the x will be something like this. So it will be very closely concentrated around the mean. Even if you go slightly far away, the probability that it is going slightly far away drops down suddenly. That is a key point here. Okay, and the form that we will use is that in fact the form that we will use is I think they are the same, is the next one, but which is identical to this one. So another form of stating this is for all epsilon between 0 and 1. So earlier epsilon was in the previous form, epsilon was as a fixed quantity, but now epsilon is a 0, it is something between 0 and 1. So now what is the probability that x is 1 plus epsilon above mu, and x is less than 1 minus epsilon times mu? Again, there are two forms here. When the first one, what is the probability that x is 1 plus epsilon above mu? It is e power minus epsilon squared divided by 3 times mu, and So right, and the probability that x is at most 1 minus epsilon times mu is e power minus epsilon squared by 2 times mu. So the point that one has to note is the expectation of x is mu. What Chernow bound is saying is, what is the probability that x is 1 plus epsilon times more than the expectation, and this happens to drop off significantly. So the point here is that when n is large, right, when you, so this you can do a simple experiment and kind of convince yourself. Let's say you toss a coin 10 times. We usually expect heads and tails to come roughly half of that, half of the times, but you may get, let's say, sometimes you may get 6 heads and 4 tails, right? And that is not really that surprising. You can just toss it and try for yourself. Sometimes you may get, even though it's less likely, you may get 3 heads and 7 tails, right? But it's unlikely that all 10 of them are heads, right? But now let us say you repeat the experiment for, let's say, 1,000 times, or let's say 10,000 times. If you toss a coin 10,000 times, it's very, very unlikely that you will see 6,000 heads and 4,000 tails. What you will see is that most of the times at least 4,900 heads, and between 4,900 and 5,100 you will see both heads and tails will be between 4,900 and 5,100. It's not going to be like vary that much. So the point is that when you repeat these experiments more and more, when n becomes more, then the mean is going to be more and more concentrated around the expectation, right? Or the sum is going to be more and more concentrated around the expectation, which is what is happening here, right? So now what we do is, again, let us come back to what we set out to do. We had a machine that accepted x, that is in the language, with probability 1 half plus px, half plus 1 by px, and for x is not in the language, the probability of acceptance was at most half minus 1 by px. What we do is, we will exploit the Chernow bound. How do we do that? By repeating this machine multiple times, like with any other boosting. We repeat this machine multiple times, and then we see the majority outcome. So if the majority is accept, we will accept. If the majority is reject, we will reject. Okay, so the number of times that we will repeat is this quantity, rho times 2 times p square x times natural logarithm of 4. So why we get this number, we will see. So basically we will do a bunch of calculations, and at the end, if you put this quantity, it just works out to be the correct quantity. Okay, so m star is the machine where we repeat m this many times, okay, on the same input x. And we set m star to accept if the fraction of accept is greater than half. Okay, so so now we set rho again. What is rho here? Rho is the probability that xi accepts, and this we know to be at least half plus 1 by px. Now what is the probability that m star accepts? M star accepts when, sorry with this trouble, m star accepts when at least half of the trials accept. So so xi will be 1 if that the ith trial is accept. So right, okay, so what is the probability that m star is not accept? Right, m star is not accept when strictly less than half the trials don't accept, or maybe less than or equal, like maybe half, it is not strictly less than, so less than or equal to half trials don't accept, right? Or in other words, at most half the trials accept. So the number of accepted trials is less than or equal to half the total number of trials. So half is the tx is the number of trials, right? And xi indicates each trial whether it accepted or not. Xi is 1 when a trial accepts and 0 otherwise. Okay, so again the next line I'm dropping in this line, the second line I'm dropping the summation limits I equal to 1 to tx. and I am writing it in a different way. So I am writing half as so half Tx, I am writing it as rho minus 1 by Px, right? Because from this quantity we have half plus sorry 1 by Px to be less than or equal to rho. By rearranging we get that half is less than or equal to rho minus 1 by Px, right? So this is what we have here. So we replace this quantity, and then we can take the rho Tx outside by adding another rho here, another rho in the denominator here, and now we have this form. So we have so notice that rho Tx is the expectation, right? Rho Tx is the expectation. This is the expectation. So now Chernoff, if you apply Chernoff this form, what is the probability that x is less than or equal to 1 minus epsilon times the expectation? So epsilon here is 1 by rho times Px, which is nothing but e power minus epsilon squared divided, sorry, e power minus epsilon squared by 2 multiplied by the expectation. So e power e power 1 by so you can work that out, it is rho square p square, and then multiplied by the expectation, which is this rho Tx. So the rho 1 rho cancels and divide by 2, and you have this quantity, the denominator 2 times this, and if you set Tx to be this quantity, it is exactly this denominator multiplied by natural logarithm of 4. All that remains is a minus natural logarithm of 4, so it is 1 by 4. So what we showed here is that when x is in the language, the probability of this repeated, the boosting machine not accepting, is at most 1 by 4. And same calculation, similar calculation you can do when x is not in the language, and you will again get this 1/4 probability, right? So basically we are repeating and then showing that the resulting machine, right? Again, we use only polynomially many repeats. P is a polynomial, the number of trials is rho times 2 times p square x times log 4. So rho 2 log 4 are constants. P is a polynomial, so p square is also a polynomial. So so the number of repeats is still polynomial. So m is a polynomial time machine, m star is also a polynomial time machine because running time is just multiplied by a polynomial, and the probability of accept when x is in the language is at least 3/4, and probability of accept when x is not in the language is at most 1/4. Hence which conforms to the requirements of the BPP machine, right? Hence hence even if we had the probability of acceptance just above half and just below half, right, we could boost it to show that we could boost it to get a BPP machine, right? So this is this is standard kind of boosting, but I thought it will be good to go through because it is good to know this, and especially if you are interested in randomized algorithms and study it, you will find this very helpful, right? So that's about the boosting of BPP. Again, I already said that BPP is contained in PP, right? BPP is contained in PP. And another point is that one question that one may ask is BPP equal to P? Right? It's widely believed that it is equal to P, but there is no proof known. In fact, it is not even known if it is equal to NP, right? Sorry. Even this is not known. Is it contained in NP? Even that is not known, right? Whether BP is contained in NP, this is not known. So there are many open questions. So widely believed that BPP is equal to P, but there's no proof yet, right? And it is, so whenever people think of randomized algorithms, right? So Papadimitriou, whenever people think of randomized algorithms, people I think the most natural class is BPP, because it's natural to have two-sided errors and some error probabilities in both cases, rather than, let's say, one-sided error, only one kind of error, etc. So in fact, Papadimitriou says this in his book, right? It is the most comprehensive yet plausible notion of realistic computation. So notice that he doesn't say realistic randomized computation, he just says realistic computation. So hence it's a very interesting class, it's a very fundamental class, right? And the last thing I wanted to say today in this lecture is about comparison between different randomized classes, right? And I'll start with NP just to get some baseline going. Let me just check on the time. So perhaps I'll just do this in the next lecture. Okay. So I'll just summarize this lecture. We defined PP, the fact that it does not have a gap, right? It does not have a gap. We showed that NP is contained in PP. We saw why BPP is contained in PP, and then we saw the boosting of BPP and using Chernoff bound. And I mentioned that it's a very important technique that is used a lot in randomized algorithms. And in the next lecture, we will see the comparison between different randomized classes.